Hello everyone, welcome to HPC Knowledge Meeting. My name is Joshua Mora. I work at NVIDIA at the architecture team, optimizing training workloads at larger scale. This is a talk about performance analysis and optimization of GPU-based larger scale deep learning training workloads. I will show this methodology on ResNet 50. Below is the agenda for this tutorial. The objective is to do the software optimizations for deep learning training workloads at larger scale. We have done this work with more than 1,000 GPUs. In order to achieve that objective, we perform an end-to-end analysis which would require an understanding of the algorithms, an understanding of the software layers, which we are going to go a bit in detail for the case of ResNet 50, and an understanding of the hardware subsystems in the DGX cluster. Once that is understood, we would run and profile the application at scale in the clusters. This step generates lots of profile files which contain information that we have to post-process in order to analyze more easily. For example, tagging the profiles can help identify both the execution stages and the areas with bubbles of no execution. Then we can feed that information into a set of execution models, which guides the trade-off analysis that affects to the large-scale execution. To conclude the tutorial, we will cover the most important optimizations applied to ResNet 50 workload that lead to improved performance at large scale. As part of the end-to-end analysis, we're going to start then by providing an overview of the architecture of the software layers in the ResNet 50 training workload and the hardware subsystems involved in the DGX cluster when we run the workload at scale. From bottom to top, and from software perspective, we start with the system software, which can be BIOS, drivers, host operating system. That is the first layer that one could think to optimize. Then we move up into the user application and software layers. In our configuration, we're choosing to run the application within a container. There we have a set of libraries that will be used by the application, such as cuDNN, the map library dedicated to deep learning, the Nickel communication library for both inter-node communication via NVLink and inter-node communication over InfiniBand. Also, we use MPI library for launching the application and for communication among the processes, both inter-node and inter-node over InfiniBand. We have also Hotbot library that uses both Nickel and MPI, which is used for a set of deep learning frameworks to ease the sharing of neural network data among the GPUs. Above those libraries, we are implementing ResNet 50 on top of the MXNet deep learning framework. Finally, on the top layer, we have the scripts that launch the containers that contain the workload, that profile, if needed, with NVProf and NSys while the workload is running, and that log the output of the execution and profile files. On this slide, we're going to cover some software architecture details related with the deep learning framework of MXNet for the configuration of ResNet 50 training workload. What subsystems are being used within a DGX node and a high-level diagram of a DGX cluster. On the left, I summarize the set of threads that are spawned by each MPI process that will hand out work to a set of cores, and that will offload to accelerate the computation to a single GPU with a specific InfiniBand link. Each thread has a specific purpose, and ideally, you would want to have a dedicated core for each thread. If you have more threads than cores, you would oversubscribe some cores, and that could lead into CPU congestion, which would slow down the issuing of computational kernels offloaded to the assigned GPU, which in turn would create a non-deterministic execution variability with negative impact at large scale. In this particular case, for ResNet 50, a total of 8 threads have to run within a group of 6 to 10 cores on DGX2 and DGX1 respectively when feeding a given GPU. Looking into the block diagram, on the bottom left, during ResNet 50 training, the MXNet framework executes the graph of operations in the cores, which reads images from the disk, preprocess them, and send them to perform a set of convolutions into the GPU. How about instructs from the cores to the GPUs what gradients are ready to be reduced across the GPUs in the cluster, where the communication happens both via NVLink and via InfiniBand. On the right side, we show a representation of both a DGX1 and a DGX2 cluster, with a top-of-the-rack InfiniBand switch with more than 1000 voltage GPUs. Now that we have covered the basis on the software architecture and described the subsystems involved in the execution of the training workload, let's look next at a large-scale run where we have enabled the profiling of the execution, and let's visualize what it would look like the profile data for just a few of those GPUs out of 1000 GPUs in action. The first impression that one can get while trying to digest this slide is just too much data to go over, and to figure out where to go hunt for optimizations. On the left, from top to bottom, we have listed a set of GPUs, 0, 1, 2 that are within a DGX node, and the others further down until the last GPU involved in the run. Here it is a 96 DGX2H nodes with a cluster of 1536 GPUs. Each GPU runs concurrently a bunch of streams issued by different CPU threads. One can observe as we look from left to right, as time progresses, the execution of kernels within each epoch. Occasionally, we see gaps or bubbles of no execution, both within a particular GPU and also across all GPUs. Notice that the location of those bubbles does not follow any execution pattern in time. In fact, from run to run, those bubbles do not show up at the same point in their execution, but they certainly happen a lot, and they can cause meaningful inefficiencies at scale. So, how do we reproduce and measure those gaps in a consistent way so we can start looking for optimizations? Can we post-process the profile data of all the GPUs so it can easy the analysis? We will show that next. We start by tagging the code around the execution stages within a training step. We can tag using NVTX or by simply knowing the names of functions involved at the different execution stages. This will facilitate later on the post-processing of the profiles of each GPU involved in the run at larger scale. In the following top and bottom diagrams representing two different execution models, we can see the execution stages are tagged. A step starts with the forward phase. The forward phase cannot start until the images are ready, prepared, such as decoded, augmented, and cropped. Once the forward phase is done, it starts the backward phase where local gradient contributions are computed. At the same time, one could start pre-processing the next batch of images to be consumed later on by the forward phase of the next step. This pipelining optimization is shown in the bottom diagram. Additionally, communications related with the reduction, once the backward stage has completed as shown on the top diagram, could be overlapped instead, as shown on the bottom diagram, reducing further the time that is needed to complete the step. There would be still some exposed time per step, and we will go in more detail later on. But we can see already a way to pack the execution per step by running concurrently pre-processing and overlapping the communication as backward phase progresses. At this point, we can go back again to that ugly representation of executions, zoom into a few training steps within an epoch, and try to identify those execution stages aforementioned. We can start appreciating better now how the execution happens and where some of those gaps are happening. For example, this is an execution where DALI, the preprocessing library, does the preprocessing pipeline concurrently with the beginning of the backward stage. Here we have it. Here's DALI, and this is the backward. We can see also that the reduction operation is done after the backward stage is completed, but the communication stage does not seem to happen right away. There is a bubble of no execution happening between the backward stage and the communication stage. What is happening in here is that the GPUs we're picking to represent their execution at this particular set of steps are not showing that there is another set of GPUs that are delayed in the execution of the forward and backward phase. So it is difficult, if not impossible, to realize of this scenario unless you look at all the GPU profiles at once at each training step for the entire duration of the profile session that could have 1 or 2 epochs. Hence, the need to post-process the set of profile files to identify those issues. With that approach, we find easily when those issues are happening and what GPUs matter for the gap analysis, so we can narrow the inspection of profile data to a couple of profiles out of 1,000 profiles and to a particular training step. Once we pick the offending profile of a GPU and the training step, it is much easier to investigate in the vicinity of the profile what causes those execution delays. For example, here we show the profile information of just one GPU on a particular time step. Using NSYS as profiler and NSIDE for visualization, we can see that at the training step of interest, there is already delays towards the end. One of the benefits of these tools that we will exploit later on is the capability to see what happens both on the GPU and on the CPU. So we could see what prevents the GPU kernel from running because the CPU being busy doing something else. We can see the tagged execution stages and where those bubbles of no execution are happening. In this particular case, it is worth noticing the MXNet framework has NVTX enabled, which allows for post-processing the tags and narrowing the analysis beyond the execution stages, all the way to the functions within each of these stages. Once we have the code tag, we can proceed to create some execution models and feed them with the profile files originated from the analysis of 1,000 GPU profiles that came from the execution at scale. As you can see in this slide, we have two execution models being pictured. On the left, we have a rather ideal execution at scale where all the execution stages within a training step line up well in time, and all the GPU executions of stages progress independently and deterministically, where they all reach at the same point in time to the synchronization events, or the transitions from one stage to another. On the right side, we have the reality, variable executions, start and end of each phase at their own pace in a non-deterministic behavior, but still subject by execution dependencies, which we are going to leverage for our understanding of what is reasonable and what can be optimized. It becomes therefore a statistical data science problem where we need to do some tail analysis for a given execution stage in order to identify where those delays happen and to assess through a statistical metric such as the mode what is the reasonable time for an execution stage to complete. Reducing the tail would help reduce the mode as well, and that is a conservative way of assessing the impact of the performance optimizations at scale within the variability of the execution. We define the drift at each edge of an execution stage for a given training step as the delay of the latest GPU to reach that execution point and the earliest GPU to reach that execution point across all the GPUs involved in the run at scale. Any imbalance, any glitch, any delay at any stage will be reflected in the drift metric. A GPU being delayed at the start will cause usually the same GPU being delayed at the end of that execution stage, which could as well delay the start of next stage, given the execution dependencies. We can look into what is normal or accepted delay and what is not a tolerated delay and how it affects to the overall scalability, which would indicate an area of focus on the large scale optimizations and what is the upper limit benefit of that optimization at scale. In regards of the execution of stages and their dependencies, we can see in the following diagram that the forward stage is followed by the backward stage, and as soon as backward stage is started, we can execute concurrently the pre-processing of the next batch of images to be consumed by the forward stage of the next training step. And as backward step progresses, we can start running concurrently the reduction operation of the already computed partial gradients. Finally, the weight updates can happen once backward stage is completed and as soon as gradient reductions in the communication stage progress. In this diagram, we would like to mention that there is a region of execution where DALI, the backward phase, and the communication phase will fight for the GPU resources, hence interfering each other in the respective executions. That is indeed a source of execution inefficiency at scale that we will go over later on and quantify accurately through this methodology. Given that there will be bubbles of no execution happening here and there, not precisely but mainly bound to happen between the end of the backward stage and the beginning of the weight update, we're calling it the exposed stage. The objective would be to reduce as much as possible that exposed stage, to pack further the execution of each training step. In this screenshot, we have captured the output of a little script that we have created to parse and process those thousands of profiles after a given execution at scale, generating a set of charts that quantify the time of each stage, the drift, and the percentage of time of each stage with respect to the total time of the training step, and across the many steps of few epochs. We can do this analysis for a given optimization, for a given execution model, and to measure in a statistical manner accurately the effect of such optimization, and to be able to explain the benefits of it as well by looking at the reduction of drift and the mode. NCIS provides the capability to export the profile data using SQLite format that can be later on browsed and parsed easily with SQLite API available in a wide range of programming and scripting languages. This one is done, for instance, using Python. The SQLite schema for the profile data is provided in the documentation of NCIS, but it is as easy as querying the database for a particular tag or a function name, all the entries for the start and end of it, across all the training steps and epochs, across all the GPU profile files. In the following slides, we're going to show multiple configuration of executions that the profile data at different scales summarized and what those metrics of execution look like. While some optimizations could look counterintuitive, the statistical methodology provides the measurements and insight needed to understand more easily the trade-offs that affect the parallel efficiency at scale. We will spend some time explaining this slide, and we can go hopefully much faster in explaining and analyzing the more interesting configurations at larger scale in some of the forthcoming slides. We can get warmed up on this methodology with a small scale configuration of just a couple of digits, 2 nodes, and without communication overlap. We proceed to get the execution and the profile done, which will generate a total of 32 profile files. That is, 2 nodes times 16 GPUs each. We just profile a couple of epochs which contain plenty of training steps since we're running a mini batch per GPU of 39 images, which is the batch size that we will use as well at larger scale due to algorithm constraints. So we will not change the batch size across all configurations shown on this tutorial. Let's look at the table to start with, and please refer to the diagram of execution of stages for better understanding of what we are timing. The overall time for the training step end-to-end was around 34.4 milliseconds. Out of those 34.4 milliseconds, most of the time is being spent in the backward stage. Here it is around 55% of the training step. On the top right histogram, we can see the distribution of timings of the backward stage across all GPUs and across all the hundreds of training steps that have been profiled during a couple of epochs. You can see the narrow shape with little tail. Some outliers, like the one shown here, due to glitches, have to be manually or automatically removed in order to get reasonable numbers. The mode for the distribution of timings in the backward stage is around 18.9 milliseconds with executions that can take up to 20.5 milliseconds. That would be the tail for this backward stage when running the workload with only 2 DGX2 nodes. On the bottom right histogram, and knowing that we have not overlapped the communication with the backward stage, we have a distribution of timings of the communication with a mode of around 2.5 milliseconds, which will happen within the exposed execution stage labeled in here as EXP, that we have measured as well and written down in the table. Out of that exposed time of 4.1 milliseconds of the training step, we spend around 2.5 milliseconds on the communication. So those numbers make sense. That is, the communication time has to be at most the exposed time. After that comes the weight update, which accounts for something in the range of only 3.5%. Ideally, we would want to get rid completely of that exposed time by overlapping the communication with the backward stage, so we can reduce as much as possible the exposed time. From parallel efficiency standpoint, we can assess that 4.1 milliseconds of exposed time minus 2.5 milliseconds spent on necessary communication for the reduction of the gradients leaves only 1.6 milliseconds of no execution out of the 34 milliseconds of the total time of the training step. Percentage-wise, 1.6 milliseconds out of 34.4 milliseconds is 4.6% of inefficiency. In other words, this execution has a parallel efficiency of about 95.4%. That means a very high parallel efficiency. We can also see that despite the variability of the execution of stages and the way we are choosing statistically to measure each stage, we can assess easily the error in this methodology by adding all the stages individually and comparing it with the back-to-back measurement of the training step, which is below 1%. Therefore, this methodology is providing some confidence. Let's look now at a configuration with the same number of nodes, but we do the communication overlap. We are also running a non-optimized pre-processing stage that taxes the backward stage and that can also stall the forward phase of the next training step. The overlap of communication stage will also interfere and tax the execution of the backward stage. Do we get to improve the performance with such execution model at this small scale? The answer is that it does not improve the performance with respect to the configuration shown on previous slide. Training step time increases from 34.4 milliseconds to 37.8 milliseconds. Forward stage remains untouched, but backward stage takes now longer due to the taxing of or interference of DALI and nickel when trying to use the same resources that the backward stage is requesting. We have measured an increase from 19 milliseconds to 21.9 milliseconds. That means an increase with respect to the total time from 55% to 58%. We can also observe on the top of the histogram the tail on the right side growing up to 28 milliseconds, making the mode for this time distribution to increase from 19 milliseconds to close to 22 milliseconds. Notice as well new distribution of the elapsed time for the communication at the bottom histogram. Now it does not take about 2.5 milliseconds, but about 20 milliseconds or so. Is that wrong? No, it isn't. It does make sense. Here it is why. Due to the execution dependencies, we are allowing the communication to happen in chunks with a large time budget from the early start of backward stage and to finish with the last group or chunk of gradients after the backward stage has completed. Therefore, the last reduction will be very little and network latency bound rather than network bandwidth bound. Our hope, though, was to get a positive net effect of reducing substantially the expose time that we had shown on previous slide. But the network latency of last reduction is quite the same as the expose time we had and the non-overlap case and the increase in the timing of the backward phase, which pushes out the last reduction, cancelling the potential benefits of the overlapped communication. Now we can jump into a case study of a larger scale. The configuration at hand is a 32DGX2 node run that will use 512 GPUs, so it creates during the profiling a set of 512 files. Considering that each profile file could be about 100 megabytes worth of profile data, we are starting to post-process tens of gigabytes worth of profile data for a single run. We start by exposing completely the communication, since on the two-node run seemed to be better than the overlap case. We run the scripts, we get the numbers, and we can see, for example, in the histogram, the communication taking about 4.5 milliseconds in the mode. That makes sense since the expose time is 5.5 milliseconds, which is about 15.4% with respect to the overall training time that has increased from the 34.4 milliseconds to now 39.19 milliseconds. Since we're running the same batch per GPU as in the case of the two-node run, all the execution stages take about the same as on the first scenario shown without the overlap. The reason for the increase in the overall time is because the communication time which is exposed has increased from the 2.5 milliseconds on two nodes to about 4.5 milliseconds in 32 nodes. From execution efficiency standpoint, 5.6 milliseconds of expose time minus the 4.5 milliseconds of reductions leave out 1.1 milliseconds of non-execution, which is a 3% with respect to the total time. The expose time has increased and the reduction time has increased. The parallel efficiency has decreased a bit, but we're running with a way more compute nodes and GPUs. Let's analyze now the scenario of a 32-node run with communication overlap and DALI optimized. To start with, we can see that the end-to-end time has increased modestly from the 34.4 milliseconds on the two-node run to 34.9 milliseconds on the 32-node run. That is good then, since it allows to increase the node count without incurring into overheads when running at larger scale. This allows for an almost linear increase in the processing of images per GPU for all those GPUs. In this case, we can see in the histogram the distribution of the communication time which fits with the allowed budget of the backward stage. If we add the backward stage plus the expose time, we have 20.85 milliseconds plus 2.78 milliseconds equals 23.63 milliseconds, and the communication mode is around 18.5 milliseconds, well within that budget. Considering the tail effects in the communication up to 20 milliseconds, it is still well within the time budget. It is therefore important for larger scale runs to overlap the communication with the backward stage in order to sustain the throughput of each GPU during the training. To summarize our trade-off analysis and findings, we see on the bottom diagram the configuration with no overlap where the communication is fast, about 4.5 milliseconds mode. but it is completely exposed after the backward stage. The end-to-end training time was 36.2 milliseconds. On the top diagram, we show the configuration with overlap, and it has optimized the pre-processing to not hurt the backward phase, nor to stall the forward phase in the next step. We are allowing the communication to take longer, about 18 milliseconds, as backward progresses. After multiple reductions within the step, we have the remaining group of gradients to be reduced, which is part of the exposed time. Despite the interference to make the backward stage to take longer, it would finish the weight update sooner than on the non-overlap case. The end-to-end time was 34.9 milliseconds. We will finish this end-to-end analysis with another way of looking at the problem. We have some execution variabilities that we should understand and keep under control, or even better, to try to mitigate. We show for each execution stage the drift analysis on an optimized 32-node run with communication overlap. As defined in earlier slides, for a given training step, this drift is the delta of elapsed time between the GPU that starts or ends the latest and the GPU that also starts or ends, respectively, the earliest. The green line is the drift at the start of the stage, and the red line is the drift at the end of the execution stage. If we understand the execution dependencies of each stage, it means that, for example, the drift of the end of forward stage in red on top left chart is the same as the drift of the start of the backward stage in green on the top right chart. Also, a fixed embarrassingly parallel computation not disturbed by anything will carry any drift without amplification nor damping from the start to the end of such a stage, as it can be seen in the forward stage on the top left chart and during the weight update on the bottom right chart. On the bottom left chart, we can see that while the starting of communication could vary quite a bit, the green line, all the GPUs finish at the same time as a synchronization point due to the fast reduction of the leftover gradients. So there is very little drift at the end of the communication as shown on the red line. It is worth noticing the magnitude of the variability when picking what execution stages to focus for the optimization at scale. For example, an average variability, not a peak, of 0.5 milliseconds across all training steps out of 34 to 35 milliseconds elapsed time for the training step means only a potential to optimize below 2%. We will focus next on the top right chart for the backward stage, which shows the largest variability within the drift and the amplification of the drift as we progress on its execution, as shown on the end drift with respect to the start drift. In this chart, we can see the drift for the start and the end of the backward stage for each training step profile. We can pick a particular point of interest in the drift, like the one circled in the end of the backward stage, the red line, and get from it the pair of GPUs involved in the measurement of the drift. We cannot only measure the gap or delay in the execution of the particular edge of the stage, but also pick the right GPUs that will help us understand the impact at larger scale. All the other GPUs will be represented by just those two, which is an easier task to explore through the visualization tool like nSight. In this example of a large-scale run, we see measured an average of 4.5 to 6 milliseconds of drift at the end of the backward stage. Considering that the end-to-end time for the training step is 35 milliseconds, and if we were able to eliminate the amplification of the variability during the execution of the backward stage, which means to close the vertical distance between the red line and the green line, we would reduce the training time about 3 milliseconds. 3 milliseconds of reduction of variability over 35 milliseconds that takes the training step would lead to a meaningful 9% performance improvement at very large scale, worth the focus of the software optimizations. How do we improve the execution to make it more deterministic when concurrently we are running with the backward stage, the pre-processing, and the communications? We will cover a list of optimizations applied to this workload in the forthcoming slides. The list of optimizations that we have found to impact greatly at larger scale are affinity, data preprocessing, and communication overlap. Let's explain them one by one when applied to ResNet 50 training workload. With respect to the optimizations related with affinity, we are referring to the action of pinning each piece of software to be executed into a set of specific hardware subsystems to guarantee efficient, consistent, and as balanced as possible execution. Among those things that we have to watch for, we do not want to oversubscribe resources, and we do not want to go fetch data from or send data to a subsystem that is far away or through some buses that will create inefficient flow of data through the platform. In this slide, we review again the software layers involved in the execution of ResNet 50 and whether we have to apply affinity implicitly or explicitly. One thing to remember is that setting affinity properly will help deliver the best performance and with deterministic execution. Or in other words, if applied properly, it won't hurt the performance. The affinity is usually understood from top to bottom. Being the top, the scripts that launch the application, and being the bottom, the application libraries, system libraries, and drivers. Each software layer could inherit the affinity specified from the layer above it, but sometimes we find some layers don't inheriting the affinity and we have to pass it explicitly. The script will tell MPI where to spawn processes of the MXNet application and what is the range of cores allowed to run the processes and the threads spawned from the processes. Since different threads have different functionality, we have to do the code coverage to make sure every piece of software runs on the designated core IDs. In this slide, we show through the tool of LSTopo, including hardware log software package, what resources are available in a DGX2 node. Here on the left, we have circled the group of cores that will be used for the local MPI rank 0, which will later use all those 6 cores, 3 cores plus their siblings, when hyperthreading is enabled. Some of those threads running on few of those cores will issue computational kernels that get executed on the GPU 0, circled on the top right. Next to that GPU 0, it is physically close enough the InfiniBand card 1 that the GPU 0 and the set of cores we were mentioning will use to send and receive the gradient information during the reduction operation. The entire system is partitioned with equal amount of resources, and we pin the processes and threads to those CPU cores, GPUs, and InfiniBand cards to create a balanced stress of the node when we run the workload. For example, local MPI rank 7 will use core IDs 21 through 23 and their siblings 69 through 71. The threads running in those cores will issue computational kernels only to be executed on those cores and on our GPU 7. And when needed, they will exchange data with other DGX2 nodes over the high-speed InfiniBand card 4. We can place all the affinity settings in the following script that is used at the time of launching the application. We can, for instance, specify for a given local MPI rank what cores are used, and within the application what threads are used for pre-processing data. We can also control from the script the amount of threads that the MPI process spawns, such as MXNet worker threads for execution of kernels and threads for copying data to the GPU, and hotbot threads that control the number of concurrent nickel streams, which we will get into later on. We also specify which InfiniBand card is used by the MPI rank. MXNet code uses the local rank information to decide what GPU to use from the DGX2 node from the available ones, from 0 to 15. One easy way to verify that the MPI rank that deals with a particular GPU is using only the cores we passed through the script, and that all software layers will comply with that affinity, whether set explicitly or implicitly, is by visualizing one profile from NSYS for a GPU. Say this time we're running the workload on a cluster of DGX1 nodes, the GPU 0. Based on the scripts specific to DGX1 nodes, we should only use core IDs 0 through 4 and their siblings 40 through 44. We can load the profile file created with NSYS into nSight and expand the view of nSight to look at what CPU cores are involved in the execution that is tied with the profile of GPU 0. Since NSYS is a system-wide profiler, if any process and its threads are running outside the prescribed range, we would spot it in the visualization tool easily. In here, after applying properly the affinity on all layers, we are able to double-check that there are no threads running outside the range of cores we define in the script for any training steps. This view also allows us to see if there are any cores busier than others. And perhaps we can move around the threads by pinning them to other cores within that range to balance better the usage of the cores. Realize that core ID 0 is also occasionally busier than other cores dealing with a system-related activity and system interrupts, which have to be serviced by a pool of balanced cores across the system. The intent is to prevent or reduce the oversubscription of cores that could slow down the application execution, not only on those cores, but on the GPUs that receive data and kernels to be executed. Now, let's think about the following scenario. Say we have a thread for some functionality of MXNet that runs in the wrong core, a core that is perhaps oversubscribed, used also by another thread for another MXNet process that deals with another GPU. This can happen because a piece of software is setting wrongly the affinity, and therefore threads ends up running in the wrong core. The outcome is a slowdown of that particular thread that creates a chain reaction sort of a speak that delays, even if it is a tiny bit, the execution of that GPU, but also can delay the other GPU, since all the GPUs have to progress through the execution stages at the same time, and as we have explained before, any delay or drift on one GPU will affect eventually at each training step to all the GPUs. We can see those effects as gaps of no execution across all GPUs except the one that got delayed. Having those issues happening, it is guaranteed to observe them across many steps, which will hurt the overall training time. The more GPUs we use, the larger the negative impact. Hence, the need to make sure affinity is properly set. We move to another optimization that affects the execution at scale, this time related with the data preprocessing. This slide is a representation of a bunch of GPUs from top to bottom, executing kernels from left to right. Each row represents a stream for a different task grouped in the training steps. If we zoom in for a given GPU and for a set of 5 training steps, we can see that there are some bubbles of no execution that could be large enough to halt the entire set of GPUs until the preprocessing for a specific GPU that deals with a large image with high quality goes through all the pre-processing work that needs to be done. If a forward stage gets delayed on a given GPU because of not having the pre-processed batch of images ready, the backward stage for the not delayed GPUs can do some progress, but eventually they will halt when a nickel operation will request to have all the partial gradients reduced in order to perform at the final stage the weight update for any GPU. So these non-execution bubbles or gaps are halts that arise from the lack of pre-processing speed. If we had enough computational resources that we could allocate for the pre-processing, that would be an easy solution. If we had enough resources, we can easily solve the problem by prefetching more batches for the following training steps and pre-processing them. That is, decoding, augmenting, and cropping, so they are ready for when the forward stage kicks in. If we do not have enough resources, prefetching can help a bit, but you still end up having the same issue with less frequency. If we run the workload at larger scale, in order to guarantee convergence, we have to run a smaller batch per GPU. That means that the preprocessing per step goes down, but it also goes down the execution of all the stages of the training step for the smaller batch. Due to some fixed latencies in dealing with the I/O, it is difficult to keep the preprocessing to take less than the training step. So increasing the prefetching is eventually not helping, and we have to focus on making faster the preprocessing so it does not put on halt the executions. That is where DALI comes to the rescue. In the next 3 slides, we'll go over the stages in which DALI preprocesses the batch of images efficiently enough to go faster than the processing of the training step. Being precise, DALI has to process a given batch which will contain the largest set of images, and it has to process them faster than the time it takes to execute the backward stage plus the expose time plus the weight update, so it can make available the images preprocessed to the forward stage of the next training step. This is the same as saying we are only prefetching and pipelining the pre-processing of one batch of images with the execution of the training step. The first stage is to shuffle the images that we want to put into the batch of images that we will pre-process. This is a lightweight stage that happens in the CPU side. Each pool of computational resources deals with its own batch of images. The next step in the pre-processing is to actually fetch the shuffle images from the set of disks that are in RAID 0 on the DGX nodes into the CPU memory. We name this the CPU stage. Once the images are loaded in memory, we decide which ones are heavier to process than others, and we decode them from JPEG to RGB format in both CPU and GPU. We decode the heavier ones on the GPU side to speed up the decoding. We name this step of the pre-processing a mixed stage because it happens on both the CPU and GPU. This is, by the way, the most compute-intensive one of the pre-processing steps, and it is therefore the step that could compete for resources on the GPU when the backward stage and nickel are running at the same time, slowing down a bit the execution of the backward stage. The final step of the pre-processing is a lightweight one where we perform the augmentation, consisting in resizing and cropping, which is performed all of it in the GPU side. This is then a GPU-only step. This is a recap slide for the pre-processing steps and other challenges that yield to delays. For any given GPU, the forward stage cannot start until it has its own batch preprocessed: shuffle, fetch, decode, and augment. All GPUs will eventually move together from forward to backward stage, and all GPUs will eventually reduce gradients together and update weights together. In order to have training steps synchronized with little or no delay across all GPUs, like the one shown in here, we need efficient execution of the preprocessing with minimal interaction during the backward stage, so it can help in the parallel efficiency at larger scale. Despite we can optimize the decoding to make it fast enough, we are still experiencing another challenge. While each GPU ingests batches of the same number of images, each GPU ingests different images with different image sizes, quality, and therefore different processing requirements that yield to processing imbalances that can create delays and affect the scaling efficiency. This is not unique to image classification neural network. Other neural networks face similar data ingestion and pre-processing imbalances. We are getting close to the end of this tutorial. The last optimization we're going to cover that affects larger scale efficiency, which is the communication overlap. In this final slide, we want to get into some of the details of the way we perform the overlap communication and the difference in the execution of the communication itself when done fully exposed versus overlap with the backward stage. On the top diagram, we have the not overlap version. We can see some exposed region of no execution bubbles before nickel gets to execute. This is due to being a GPU slightly delayed for the several reasons mentioned in previous slides. In this diagram, we choose to not show the GPU streams used by DALL-E by running what we call a synthetic image generated on the fly. We look next at the behavior of the execution of nickel overlap and pipeline with the backward stage. Hotabot is allowing quite a bit of flexibility in the scheduling of the execution of reductions when combined with the MXNet network framework. To start with, MXNet processes operations of the graph that represents the computation of the neural network during forward and backward in bulks controlled by a pair of environment variables named forward bulk and backward bulk. The default setting is to perform 15 operations in a bulk. Within that time, we cannot schedule any other work, which limits the opportunities to launch multiple concurrent streams. During the forward phase, we do not have to run anything in parallel within a given GPU, so there is no need to chop the operations of the forward phase, and we can increase the bulk for forward to do all the graph at once. During backward stage, though, we tune the bulk to provide enough tensors to Hotabot to make it worth the reduction. To be more specific, we split the total work of the backward stage, which contains about 160 tensors, in 8 bulks of 20 operations, and concurrently we run Hotabot to pick those 8 groups of tensors to match the IB network latency of low latency nickel kernels, which are between 3 to 4 milliseconds. We run a total of 16 nickel kernels in parallel with 2 nickel streams. Here is one stream and here is the second stream. 8 for the floating point 16 and 8 for the floating point 32. The exposed communication is the last group of leftover tensors, which are reduced by the last concurrent nickel calls, taking only 3 to 4 milliseconds. With that approach, we achieve a decent overlap, and we reduce the exposed time with non-execution bubbles. The net effect is the reduction of the training step at larger scale. With that, we conclude the tutorial, where we hope you can apply similar, if not the same, end-to-end analysis and optimizations as the ones explained to your own neural networks. On our end, we can apply this methodology to other neural networks that we are optimizing for training at larger scale. We would love to hear your feedback.